Okay, we are back, and hopefully we won't have any more interruptions going on here. Okay, so uh, so let's just get back into it here. Hopefully you guys can all hear me. I've got my laptop down here so that I can see the any questions that you guys have. So I believe where I left off was with, so we're gonna real quickly go over Redox. We'll get into, and then we'll just go into moles and stoic. I probably think the best thing, just to make this review focused, so that it's the best, so we're not just jumping around all over the place. I'm just gonna start at the beginning of the semester. We're just gonna work our way through, and after about an hour or so, wherever we are, that's where we will end up. Okay. So I've already gone through the types of reactions and tricks for balancing, and really the only other main issue then is dealing with the concept of redox. Okay, so if you recall, most, or not most, but all single replacement reactions are considered redox reactions. And for redox, remember that is short for reduction oxidation. So reduction is gaining electrons. So when it gains electrons, that means the charge goes down. Okay. And then for oxidation, oxidation is losing electrons. And when we lose electrons, the charge goes up. Okay. So let's take a look at probably my favorite redox reaction, which is actually one of the ones that we did in the lab, which is, so if we take, sorry, wrong way. So if we take silver plus copper nitrate, or copper 2 nitrate, it will give us silver nitrate and, wait, yes. Okay, so wait, no, I just totally wrote that backwards. That's embarrassing. Let me try this again. We started with a piece of copper and added in the silver nitrate, which then gave us the copper 2 nitrate and silver. Okay, so here is our redox reaction. We can balance it if we want, but balancing doesn't change the way we identify what's reduced and what's oxidized. Okay, so what I'm going to do is I'm going to look at the oxidation numbers, or basically the charges of all of the elements here. Okay, so copper is an element, so it has a charge of 0. Over here, silver is an element, so that also has a charge of 0. Then when we look at silver nitrate, okay, nitrate is the polyatomic ion, NO3, nitrate, which is on the backside of the periodic table, which you will be allowed to use. You'll be allowed to use the reference chart, all of that stuff, okay? You just have to make sure that you know what's there and what you're actually looking for, okay? So silver has a charge of +1, nitrate is a charge of -1, and then on the other side, so nitrate is still -1, but since there are 2 of them here, that's going to then give copper a charge of +2. Okay, so now when we compare the left side to the right side, well, copper is going from 0 to +2, so that charge is going up, meaning copper is the one being oxidized. Silver is going from +1 down to 0. Okay, so the charge is going down, so that means it's the one being reduced. So silver is reduced. Nitrate is -1 and -1. It stays the same. So we're good. Okay. The other trick to figuring out what is oxidized and what is reduced is by taking a look at just the overall equation and recognizing that reduction also means purification. Oxidation means corruption. Okay, so Silver is the one going from a compound to being an element. It's being purified, meaning that silver is the one being reduced. And then copper is going from being a pure element to going into a compound. So it's being corrupted, basically. So it's the one being oxidized. So it's a very simple, easy way to figure that out. So if I give you a reaction, like, say, if we have iron plus magnesium carbonate, and then that becomes, on the other side, iron, sorry, that should be a 2, carbonate with a 3 plus magnesium, I could very quickly and easily say, all right, so magnesium is the one being reduced because it's going from a compound to an element. Magnesium is the one being reduced. Iron is the one being oxidized because it's going from an element to a compound. Okay, so that is redox reactions. And really then when it comes to the chemical reactions kind of stuff, that's basically it. It's identifying the types of reactions. It's being able to balance equations, which, remember, it's a multiple choice test. Okay, so all you got to do is just pick the one that actually does work. Okay, and then doing some redox stuff. Okay, I know there's a much longer list of things on if you take a look at the target list for chemical reactions, but ultimately that's really what it all boils down to. Okay, so let's move on to moles and stoichiometry. Okay, now for moles and stoichiometry, remember there was the whole Molar Express thing that I gave you, the little train track to help you remember what all you got to do. Now for this, I cannot guarantee you that you will have this provided for you because it's not actually on the reference chart material. Okay, so if you want to be able to use the Molar Express, then you do need to memorize this part so that you can then write it down on the scratch paper that's given to you, and then that way you've just got it. Okay, so there are 2 versions of the Molar Express. The first one is really only the moles. So that one, we've got grams here, we have moles here, and then here we have molecules or atoms, and then we have ions. Now, here's the thing. Now, I have not actually read through the exam, but I am almost willing to bet that we're actually not really going to need to worry so much about ions because this is just something that rarely ever gets asked. So for this purpose of this review, I'm actually just going to ignore this part. Okay, so we've got these 3 units that we're converting between, and then our conversion factor here is 6.02 times 10 to the 23rd, and then this one is molar mass, which you can find on the periodic table. Okay, so let's just do a couple of examples of how to use this. Okay, let's say, for example, that we are starting with 3.84 times 10 to the 26th power, and that is atoms of iron. And I want to know, well, how many grams is that? Well, as you can see, it's a 1-2-step process. So this is not something you can just do. You just do one multiplication and then you're done. It is a 2-step process because you can't just go from atoms all the way to grams in one step. Okay? Always take your given and put it over 1 times. So since atoms is on top here, we are automatically going to put atoms on the bottom here. So this is atoms of iron. Okay, the next unit in line is moles. So moles of iron right there. And then what are the numbers that I'm going to put in? Well, it's right here. That is 6.02 times 10 to the 23rd number of atoms for every 1 mole. Now remember, this is where students get tripped up a lot when it comes to using 6.02 times 10 to the 23rd. This is the number of atoms or the number of molecules. It is not the number of moles. The number of moles here is always 1. Okay, so atoms, moles. So now that I've got that set up, I have one more step to go. So since moles is on top here, that means moles of iron is automatically going to go on the bottom. And what's going to go on top? The grams. So grams of iron on top. And where do we go to find this? Well, we go to the periodic table. Okay. So iron is element number 26, and it has a molar mass of 55.8 grams, and that's all over 1 mole. Okay, so now when I go to multiply this, I'm going to grab my calculator, and I'm going to do 3.84 times 10 to the 26 divided by 6.02 times 10 to the 23rd times 55.8. Okay, now here's the other part about doing this. When using the calculator, do not type in times 10. All of your calculators have a special button on it that says EE. That is the number, that is the button that you push. So here I'm going to type in 3.84 EE 26 divided by 6.02 EE 23 times 55.8. Okay, now I'm not going to take the time to actually calculate this out because that's not really the point. The point is, how do you set it up, and then what do you actually type into the calculator? So 3.84 EE26 divided by 6.02 EE23 times 55.8. Now, how many sig figs should our answer have? Well, we go back to the very first number in the question, and our number here has 3 sig figs. Therefore, our final answer should also have 3 sig figs. So that's something else to be looking for in all of your multiple choices. Okay, so you just got to make sure that it's all the same number of sig figs. Okay, so that's an example of how to use this molar express. The other molar express is for stoichiometry. So the stoichiometry molar express looks like this. So we have grams number 1, we have moles number 1, moles number 2, and then grams number 2. This is molar mass, as is the last part, molar mass. And in the middle, we have the balanced equation. Okay, so ultimately, for for stoichiometry conversions, this right here, adding on the grams at the beginning and at the end, well, that's no different from this right here. So the only true stoichiometry is the stuff that's right in the middle. Okay. Hey, sweet. I got one of my DI friends checking us out. Rock on. Man, I was really glad to meet you. You guys were awesome. That was such a great time. All right. So let's get back to our stoichiometry stuff here. Okay, so in order to do this, though, we also have to have a balanced equation. Okay, so let's say we have something like, let me move this up a little bit. Let's say we've got, I'll actually go ahead and use the C3H8 plus 5O2 yields 3 CO2 plus 4 H2O right there. Okay, and let's say we are starting with 38.7 grams of oxygen, and we want to know How many moles of carbon dioxide are going to come from that? Okay, so that is a grams 1 to moles 2. So I'm going to start with my grams 1, which is this. So this over 1. Okay, since grams of oxygen is on top, that means grams of oxygen is automatically going to go on the bottom. And now what's going to go on top? Well, it's the next unit in line, which is moles number 1. And remember, the number 1 represents the substance that we're dealing with. Okay, so moles number 1 is moles of. Okay, and then what numbers do we put here? The molar mass. Okay, and remember, that's 1 mole per number of grams. So oxygen has a mass of 16 from the periodic table, but since there's 2 of them, that's 32. Okay, so I'm now here at moles 1. When I go to moles 2, I'm going to use the balanced equation. So here we go. Moles of O2 is on top, which means that moles of O2 has to go on the bottom. And what's going to go on top here? Well, moles of the second substance, which, as I said, was carbon dioxide. So moles of CO2 right there. And so now I'm going to come to my balanced equation to figure out my numbers. Well, for carbon dioxide, it's 3. For oxygen, it's 5. Okay, so then when I actually then go and do the calculation, 38.7 divided by 32 times 3 divided by 5. And how many sig figs should I have? Well, my original number here has 3 sig figs, so I'm going to have 3 sig figs. Okay, so for stoichiometry and also for the moles conversions, it really just comes down to knowing how to set it up. Just remember, whatever unit is on top must automatically go on the bottom of the next one. Well, what unit goes next? Well, it's the next one in line on the Molar Express as you try to figure out, what's going on. Okay, and then you just fill in the blank spaces with the numbers that the train track tells you to fill in. Okay, now with stoichiometry, there's a few additional things that that we can ask you. So in addition to just saying, okay, here's this value, convert it, we can also apply that by saying, what is the limiting reactant? What is the theoretical yield? And then we could also then take that one step further and say, well, what is the percent yield? Okay, so a limiting reactant question is going to have 2 reactants. I mean, it has to, or I mean, sorry, 2 givens. Okay, if there's only 1 given, then it's just that one conversion and then you're done. If you have 2 givens, then that's your cue that, okay, this is a limiting reactant question. And remember, by definition, the limiting reactant is the one that makes less. Okay, so let's say using this same example right here. Okay, so I started with this given, that reactant. So let's say we also happen to have 15.0 grams of C3H8. Okay, well, we're going to convert it into the same product over here, so carbon dioxide. So I'm going to do the same thing. Okay, so grams of C3H8 goes on the bottom, mole of C3H8 goes on top. Remember, that's always 1 mole there. So for the grams, I'm going to go to the periodic table. So carbon has a mass of 12. Well, 12 times 3 is 36. There are 8 hydrogens there. So 36 plus 8, that's what, 44? Okay, so this has a mass of 44 grams per 1 mole. And then I'm going to use my balanced equation here. So moles of C3H8 is on top. So moles of, C3H8 is on the bottom, with moles of carbon dioxide on top. Okay, so then I go to my balanced equation. I have 1 mole of C3H8 and I have 3 moles of carbon dioxide. So it is now set up. Okay, so now this one I'm going to then go ahead and calculate it on out so that we can learn the whole idea of in here. Okay, so I'm going to start with this one here. So 38.7 divided by 32 times 3, 5. And what we get here is, remember, we have 3 sig figs, so 0.726 moles of CO2. If we do this one, so I'm going to do 15 divided by 44, and then times 3, divided by 1 doesn't change much, okay? So then we get 1, since we also still have 3 sig figs, 1.02 moles of CO2. Well, thank you, Noor. I appreciate you saying that. Okay. So now we compare these two here, and we can see that 0.726 is the smaller amount. So therefore, oxygen here is our limiting reactant. And the 0.726, this is our theoretical yield. Okay. Because it makes less. So for all limiting reactant questions, you're going to do basically 2 different conversions. The limiting reactant is the one that makes less of the product. Okay, so there's a limiting reactant, that's our theoretical yield. And then if I want to do a percent yield question, what I would say is something like, okay, so that's your theoretical yield. Well, you actually produced 0.614 moles of carbon dioxide. And then, so I'm going to then divide that by the theoretical yield, 0.726 moles of CO2 times 100. So for percent yield, you're going to take the actual yield, which must be given to you in the question, divided by the theoretical yield, which you just calculated from the previous question, and then times 100. Okay. And so in order to do that, let's do that one real quick. So 0.614 divided by 0.726 equals, and then times 100 at 84.6%. Okay. And that's how that works. Okay. So that's all right. So that's the moles and the stoichiometry stuff. Okay. If you need further help with chemical reactions or moles and stoic, go back onto the channel, go find those specific units. Because right now I'm just trying to do pretty much everything right here. Just kind of remind you this is everything that's going to be there. Okay. Okay, so you can go back to the channel and find out all that good stuff. Okay, so after moles and stoichiometry, then we got into all the stuff about solubility. Okay, now with solubility, there was a lot of stuff that we went through. Okay, so it started out with, I'm going to set my calculator down. Okay, so it started out with just the concept of what is water, how does all that stuff work? Okay, so remember, water is a polar substance, which means that it shares its electrons unequally. So because of that polarity, so here's the O, H, H, like this, we have a partial positive charge on the top and a partial negative charge on the bottom. Okay, so that's what it looks like. Water has all these special substances or special properties to it because it's polar. It has hydrogen bonding, so that means there's a really strong surface tension. It has the high surface heat, high specific heat, and the fact that when it freezes into ice, water expands, which means that ice floats on water. Okay, so all of those special properties that give us the stuff that that we actually need. Okay, do we need to memorize the things on the formula chart? No, you definitely do not need to memorize anything on the formula chart. You will be given that to you. What you need to do is just be familiar with the formula chart so that you know exactly what you're looking for. Okay. All right. So what can we do with all this stuff about water? Okay. So most of it really just came down to what does what does water do when it tries to dissolve something, and how do we know if something's going to dissolve in water or if it's not going to dissolve in water? So remember the phrase like dissolves like. So it has to have similar. Sorry, I'm watching a spider walk across my wall right there. That's kind of a random thing to notice. I'll get it later. um, so, uh, so like dissolves like. So water is a polar substance, meaning water is going to dissolve all of the other polar covalent substances. So if you look at a substance and you see that it's covalent, if it dissolves in water, it's polar. If it does not dissolve in water, then it's nonpolar. Okay, that's pretty much how that works. Okay, but if it's an ionic compound, how do you know if the ionic compound is going to dissolve in water or if it's not going to dissolve in water? Well, for that, we have the solubility chart right here. The solubility chart is what tells you what exactly you are wanting to do. Okay. All right, so I'm gonna just pick some random examples of compounds, and I'll show you to kind of go through the process of how to read the chart, and then we'll move on from there. Okay, so let's say we have something like sodium iodide, or if we have silver chloride. Let's say we do something like magnesium phosphate. Okay, so let's take a look at these three examples right here. Okay, so the solubility chart right here is organized by the negative ion. So in that case, or this case, it is the iodine. Okay, so we look up iodine, and iodine is in the top half section, so which means that it's usually soluble. It's soluble except when it's bonded to strontium, barium, lead, and mercury. Well, it's not bonded to any of those, so therefore it will follow the rule, and so sodium iodide is soluble. Silver chloride, all right, so the negative ion here is chlorine, and chlorine is up top here, so chlorine is in the soluble section, so chloride compounds are usually soluble, except when it's bonded to silver, lead, and mercury. Well, here it does happen to be bonded to silver, so therefore it is not soluble. It is the opposite, which is insoluble. Okay, now magnesium phosphate. Well, phosphate is down here on the bottom, which means phosphate is normally insoluble, and it is insoluble except when it's bonded to ammonium and the alkali metals. Well, remember, the alkali metals are those in group 1. Magnesium is not in group 1, it's in group 2. So therefore, this is not one of the exceptions, and it's going to follow the rule. And the rule for phosphate is that it is insoluble. Okay, it's very simple to read the chart. You just got to get, basically it's just being familiar with where everything is and all that good stuff. Okay, so that's doing the solubility of ionic compounds. Now there are a couple of other things that could come up with solubility, and that are the two equations, which let me find those equations here. All right. So the first equation is the molarity equation, which is, so molarity equals moles divided by liters. And then we also have the dilutions equation, which is M1V1 equals M2V2. Now remember, these are not anything that you have to memorize, because all you got to do is look it up, chart, and find the formulas, and then you just move on with it. Okay? All right. Now, a couple things to remember about these two equations. So for this equation, remember, there are only 3 variables, meaning for the question only has to give you So those two right there, and then you solve for the third one. But this one, though, this has 4 variables, meaning the question has to give you 3. Okay, and that's how you tell the difference between when to use which one. Here's the other main difference. This equation requires volume does need to be in liters. That's why it's an L, not a V. So it must be in liters. But over here, it just says V, because it doesn't matter if it's in milliliters or liters, as long as it's the same on both sides, okay? So I'm going to do one example of each, just to show you how each of them is done, okay? So let's say over here that we have a substance that has a molarity of 5.3, and there are, we don't know the number of moles, and it's all in 0.75 liters. Okay, so how are we going to get moles by itself? Well, now at this point though, it's just algebra. So I'm going to go 0.75 times 5.3 in order to get our missing variable all by itself. Okay, so now that I think about it, probably the better way to talk about this equation is not to do so much specific examples, but really just to remind you of just how to manipulate the equation algebraically so that you can do whatever it is that, that you need to do, okay? So this is one version of it. If I'm trying to solve for moles, remember, we're going to multiply both sides by liters. So for that, we get moles equals molarity times liters. Okay, then if we're trying to solve for liters, I'm going to divide both sides by molarity, and I'm going to get liters equals moles divided by molarity. Okay, so those are the 3 different versions of that exact same equation. Okay, other than that, it's just knowing your units. Molarity is the capital M, obviously moles is moles, L is liters. You read the question, you plug it in, and you solve. Okay, you're going to multiply or divide. Okay, now for this equation, it's actually a lot simpler because you're going to solve it the exact same way every single time. Okay, when you read these questions, it's always going to give you a little phrase that says milliliters of a molar solution. Like you have 200 milliliters of a 3 molar solution or whatever, something like that. There's always that phrase of a molarity. Look for it because those 2 numbers will always go together on the same side. And then the other number that you're missing is going to go on the other side, meaning you will solve this regardless of what the numbers are. You're going to solve it the same way every single time. Okay, so you're going to take the 2 numbers over here, multiply them together, divided by the number on the other side. That's how that particular equation works. 2 numbers multiplied together, divided by the number on the other side. And again, if you need more specific examples of how to do this, go back into the channel, go find those videos, and then you can work through the problems with me together from those videos. Okay, remember, this is just kind of an overview of everything. Okay, all right, that's the main crux of solubility. After solubility, we went on into the concepts of energy. Now for energy, here's the deal with energy. Okay, there's really only there really aren't that many targets that you have to really know when it comes to energy. Okay, so the main one is that the law of conservation of energy. The energy released equals the energy absorbed. You have to remember that. The energy released equals the energy absorbed. On our tests, there were so many questions that you guys, or also the quizzes, where you guys missed the question because you were so focused on it being a calculation and didn't realize that we weren't asking you to calculate anything, but rather to understand that the energy released equals the energy absorbed. So sometimes the answer to the question is literally right there. The number that is there is found in the question. The energy released equals the energy absorbed. And remember, energy is going to be either measured in joules, which is capital J, abbreviated by capital J, or it's measured in calories, which is abbreviated CAL. Okay, so joules or calories. When you see that number, that is energy. Okay, there's also the endothermic versus exothermic graphs. So real quick, two graphs, one that looks like this, and one that looks like this. They're similar, but there's a main difference. Okay, so we have our reactants on this side, products on this side. It's the same thing here. So reactants and products. The main difference is this right here. Here, the products are going down. So energy is being released, meaning this one is exothermic. And here, the energy is going up. So that is endothermic. Okay. Hey, we got another DI friend checking us out. Awesome. Hey, thanks for tuning in. I had a blast at Globals. By the way, if you guys didn't get a chance to go and watch my vlogs that I did, seriously, you should go watch them. There's so many creative kids that I got to meet last week. It was awesome. So much fun. Okay, back to energy. Okay, so those are the equations, I mean, so the graphs. Now, how do we actually apply that? Well, there are two equations that we learned. One of them is Q equals mc delta T. Q is energy measured in joules or calories. M is mass measured in grams. C is the specific heat, which most of the time is given to you in the question. And delta T, remember that's together, okay? That's delta T, which means change in temperature, which is measured in degrees Celsius. So if there is a, if there are two temperatures given to you, you must subtract the two in order to get your change in temperature, okay? All right, so that's pretty much that equation, okay? And you know that it's asking for this if specific heat is included. If specific heat really isn't there and it's only talking about joules or kilojoules, then it's going to be the other question, okay? But the specific heat is the key to this one. Q equals mc delta T. Q is energy, M is mass, C is specific heat, delta T is joules. And when you were solving this one, there's pretty much only two different ways that you're actually going to do this calculation. You are either going to be given these three numbers, in which case you just simply multiply them all together, okay? Or I'm going to give you the energy, and then you're solving for one of these over here, in which case what you're going to do is Q divided by whatever numbers over here. So you're either multiplying all three together, or the energy is going to be divided by the other two numbers. It is always like that. Energy divided by the other numbers. It's never the other way around. Energy divided by the other numbers. Okay. All right. So we got a question about calories. So the calories are 0.001 and the 2 calories. Okay. On that. So capital C calories, the specific heat for capital C calories is, yes, is 0.001. But for lowercase c calories, it's 1, right? Because there are 1,000 calories in 1 kilocalorie. So there's your conversion rate on that one, okay? When it comes to the specific heat of water, Now, we are going to expect you to have that one already memorized, but if you know where to look for it on the reference chart, you can find it. See if I can pull it up here. Okay, so on this side of the formula chart, down here, it gives you a conversion rate of one, right? It's right here. 1 calorie equals 4.18 joules. Now, officially, that's just giving you the conversion rate between calories and joules. But if you are wise, you will recognize that those are also the specific heat values for water. For water in joules, it's 4.18 joules per gram degree Celsius. For calories, it's 1. So you can always find your answers or your values right there if you know where to find it. Okay. But other than that, the question is either just going to give you calories, or it's going to ask you to, not calories, it's going to give you the specific heat, or it's going to ask you to calculate for the specific heat. Okay, so that's pretty much how it works. And again, if you need specific examples and specific help about MCAT, go back and find that specific video for it. The other equation, pull that one up for energy, is this one right here at the bottom. So this is the enthalpy calculation. Now for enthalpy, this one is the one where, okay, so like if you have an equation, actually there's really no point in me doing this because I'm not going to know these values right off the top of my head. But for enthalpy, it's got to give you a chart. There's going to be a chart of heat of formation values or delta H values. And so what you do is you're going to, so step 1, remember, add up the reactants. Step 2, add up the products. And then, as it says right here, it is products minus reactants. That's it. That is your enthalpy. Products minus reactants. Now remember, if the substance is not in the chart, then its value is 0. Okay? So you're going to take the values from the chart, add up the reactants, taking into account any coefficients that might be there. So add up the reactants, add up the products minus reactants, as it says on the formula chart. And then, if it is a positive value, so just like what we have with our graphs here, remember, the positive delta H is the endothermic, and then the negative delta H values is exothermic. Okay, so there's really only 3 main concepts when it comes to energy. It's understanding the graphs, which also includes the whole energy released equals energy absorbed kind of thing. There's Q equals MC delta T, and then there's the products minus reactants, the enthalpy calculations. Okay, so that's the overview on that. Okay. You will always remember being points. At least something's going to stick in your memory, right? That's awesome. Okay, so that is energy. After that was nuclear stuff. Now, I'm not going to spend a huge amount of time about the nuclear concepts here, mainly because there's like 2 or 3 questions about this on the exam, and they are so ridiculously easy. Most of the time, the answer can be found directly into, or directly in the question itself. It's like, read this paragraph about radiation. What are we doing with this? Okay, so really the only thing that I'm going to have to actually go over is just remember that there are 3 types of nuclear radiation. Okay, so you've got alpha radiation, which that symbol is He, 4 over 2. You've got beta radiation, which is the E 0 over -1. And then you've got gamma, which is that weird Y shape, 0 over 0. Okay. So if a substance is going through alpha decay, it's going to lose 2 protons and 2 neutrons, so to lose a mass of 4. If it's going through beta decay, the mass is going to stay the same, but the number of protons is actually going to go up by 1. And then for gamma decay, everything stays pretty much the same. Okay, so when you're looking at the nuclear reactions, really it's just a fill in the blank. What's missing? Which of these three things is going to plug the system and move on? Okay, there's only 3 of them. Multiple choices usually have 4 answers. Do not get taken in by the 4th random answer that's complete bupkis that means absolutely nothing. It has nothing to do with anything. Okay, because there's only 3. It's alpha, beta, or gamma. Those are the only 3 options. Don't be taken in by any of the other fancy terms that might get thrown out there. It's alpha, beta, gamma. The end. Move on. Okay. You might see a little bit about fission and fusion, but I wouldn't worry too much about it because most of the fission fusion questions are literally, here's a paragraph about the dangers of fission versus fusion and what can you take from the paragraph. Okay, so it's more of a reading comprehension thing than an actual do you know the science kind of stuff. Okay, so that's nuclear. I don't want to spend a huge amount of time on that. Let's move on, because the next major thing is the states of matter and the gas laws, and there's a lot of stuff to talk about in gas laws. So here we go. Gas laws. All right. All right. Okay, so for the states of matter stuff, most of the actual like stuff about states of matter isn't gonna be really hard because it's solid, liquid, and gas. It's the stuff that you guys have learned since elementary school. It's nothing more complicated than that. But what we're going to focus on, especially here in this review, is to gases specifically. Okay, so there were all the different individual relationships that we looked at. And I'm going to show you something it's a little different than what I actually showed you guys in class, just because this is probably the easiest way to do it quickly. And this might actually help you guys out when you're looking at everything in relation to what's going to go up, what's going to go down, is it inverse, is it direct, what, okay? When you look at the combined gas law, so remember, the combined gas law is on your reference chart, okay, so you don't have to have this memorized. But here is the combined gas law. We've got P over V N over T. So that's P1, V1, N1, T1 equals P2, V2 over N2, T2. Okay, so here it goes. If the 2 variables are next to each other in the equation, they are inversely related. So pressure and volume are inverse. Moles and temperature are inverse. If the variables are being divided, so they're on opposite sides of the fraction, those are the direct relationships. So pressure and moles, direct. Pressure, temperature, direct. Volume and moles, direct. Volume and temperature, direct. That's how you know if it's direct or inverse. If they're side by side, that's inverse. If they're on top of each other, that's a direct relationship. Okay? So that's how you figure out what's going on with each of those variables. The rest of it really is just algebra. Do you know your units? So pressure is measured in, here, I'm gonna go ahead and write them down. So pressure is gonna be measured in ATM, atmospheres, or kilopascals, or millimeters mercury. Okay. Volume is going to be measured in milliliters or liters. Obviously, moles is moles. Now, temperature. Temperature. Yes, the question could technically give you degrees Celsius, but we do not calculate this stuff in Celsius. It must be in Kelvin. And if you remember, so Kelvin equals degrees Celsius plus 273. Okay? So Kelvin equals degrees Celsius plus 273. And if for whatever reason your mind goes blank and you don't remember that in the middle of the exam, well, guess what? Check it out right here. 0 degrees Celsius equals 273 Kelvin. There you go. So that's how you remember what to do with that. Okay, so know your units, you just plug them in, and after that, it becomes algebra. Okay, so if you're having trouble with the algebra stuff, that's going to require you to go back to the videos that I've already posted, watch me go through the process. And then when it gets to the end of the video and I give you the extra practice problems to do them. Pause the video and I ask you to pause. So you hit pause, you try to work them out, compare your answers to the ones that I have. If you're still confused after going through that, you either need to type me a comment below that video so that I can help you specifically, or you need to come in before school tomorrow, because that's pretty much the absolute last time that I'm going to be able to do a review. Because once we give that first period exam, we're done. Okay. So we've got the combined gas law here. The nice thing about the combined gas law is that if the question does not have all four variables, let's say it only has two of the variables, well, that's not a problem, because you just whichever way that you need to find whatever it's going to be. Okay, so if the question only has volume and moles, well, cover up pressure and temperature, right? And then you can see that it's volume over moles. So V1 over N1 equals V2 over N2, so on and so forth. Okay, there's all sorts of different variations that you can go through, but you just read the question, you find the variables that it's talking about, move on. Okay, so that's the combined gas law. Compare that to the ideal gas law, which is PV-NRT. PV equals nRT. Pressure, volume, moles. R is the constant, and T is temperature. Now, here's the thing about PV-NRT. PV-NRT has only one of every variable. The combined gas law has two of every variable. So that's how you know which one is which, and you can look up the, figure out which equation you're going to use. Also, with PV-NRT, V here must be in liters. For PV-NRT, it doesn't matter. It could be milliliters or liters. But for PV-NRT, it must be liters. So how do you go from milliliters to liters? You divide by 1,000. Okay, that's it. Hi, baby girl. I guess Talia's trying to come in and say hi. Here, you want to come over? Come here. Come here. Say hi real quick. Say hi, everybody. Hi. Okay, and now you're going to go. Okay. There you go. Bye-bye, little girl. All right. Sorry about that, guys. All right. Bye. Okay. So where was it? Okay, so volume must be in liters. So you take milliliters divided by 1,000, and that will give you liters. Okay. Now for R, R has to be, or I mean, it's going to be on the reference chart right here. So you can do, and then you just got to make sure it pairs up with whatever unit of pressure that you're given. So it's either going to be the 0.0821, 8.31, or 62.4. Okay, so you just look it up on here, which value you're actually going to use, you plug it in, and then again, it just becomes an algebra question at that point. Once you, the chemistry portion of it is just knowing what your variables are and what your units are and where everything goes in the equation. Once it's in the equation, it's just algebra. Okay, so multiply, divide, just remember all those algebra rules and you will be fine on these types of questions. Okay. The last little thing that we could possibly happen or have with the gas laws. I'm trying to see. No, it's not actually specifically on here. Oh wait, no. Yes, it should be. It should be. Yes, it is. Is the gas stoichiometry stuff, and for that, it's right here on the chart. You've got the volume of an ideal gas at STP. Remember, STP is standard temperature and pressure. And standard temperature pressure is also right here. Standard temperature pressure is 0 degrees Celsius and 1 atm. So volume of an ideal gas is 22.4 liters per mole. So if you're at STP, then you actually don't need to use Puvnert. You just use the 22.4 liters per mole to do your conversion rate. So let me see if I can try to come up with an example of how to use that real quick here. Okay. So let's say we have this, I'm just going to do the simple one. So the 2H2 plus O2 yields 2 H2O. Okay. So we're using this equation. Let's say that we have 24.3 liters of oxygen, and I want to convert this into moles of H2O. Okay, so what I'm going to do here is I'm going to take my given, 24.3 liters of O2 over 1 times, now since liters of O2 is on top, that means that liters of O2 is going to go on the bottom with moles of O2 on top. And this is where we use that conversion factor, the 22.4 liters per mole. Okay, so 22.4 liters per 1 mole. And now that I'm at moles, I can actually do the real stoichiometry, which is just using the balanced equation here. Okay, so this portion right here, this is the gas stoichiometry. This over here, this is just normal regular stoichiometry. Okay, so if you know that from the first part, well, then you're still going to know it here. So if moles of O2 is on top, moles of O2 is going to go on the bottom. And since I'm asking for moles of H2O, that's going to go on top. Moles of H2O. And then I go to my balanced equation. I have 2 moles of H2O, and we have 1 mole of O2. So when we go to actually calculate, we've got 24.3 divided by 22.4 times 2. That's it. Okay, so just remember 22.4 liters per mole. That's your conversion to go between liters and moles. But remember, that can only work if it's at STP. If it doesn't say anything about STP, then the question is a PV equals nRT. It's an ideal gas law type question. Okay, all right. So I think that's about it on gas laws. One more unit to go through, and I think we can safely call this session complete. And that is stuff about acids and bases. Okay, now since this is the most recent unit, hopefully this is still a little bit more fresh in your minds. Okay, when it comes to acids and bases, okay, so you've got naming. Remember, for acids, there's 2 types of acids. You've got those that are binary, remember, which means 2. Okay, so those are the ones that are going to start with hydro. So if I have HCl, This is a binary compound because it's 1, 2 elements, hydrogen and chlorine. So that means I'm going to start with the prefix hydro. Then I'm going to change the ending of this to IC, so hydrochloric acid. Okay, very simple. If it's H2S, binary, so hydrosulfuric acid. Boom, done. Okay, but if it is not binary, let's say it's got a polyatomic ion in it, like the NO3 is the polyatomic ion nitrate. If you don't know that, that's okay because it's on the back of the periodic table, like so. So you got that list there. Don't forget about it. Please use it. So nitrate becomes nitric. There's no hydro because hydro is only for the binaries. And so you just say nitrate becomes nitric. So that's nitric acid. For this example, carbonate. So carbonate becomes carbonic acid. Boom, done. Okay, so that's the acids. Naming the bases is, there's no special rule, and so theoretically you should already know how to name these because it's just whatever it is: hydroxide, sodium hydroxide, magnesium hydroxide, aluminum hydroxide, whatever. Okay, so I'm not going to spend too much time on that particular concept. So we got naming, and then after naming, there's the oh yeah, all the properties, right? The properties of acids and bases, right? So you got acids taste sour, feel sticky. Bases taste bitter, feel slippery. Litmus paper, acids turn litmus paper red, bases turn litmus paper blue. They both conduct electricity because they both have ions. Acids will react with metals, bases do not, but harmful to human tissue. Your main properties of the acids and bases. Then we've got the definitions. I'm going to need to spend a little bit of time here based on the results of our test. This is where a lot of you, for some reason, like you thought that you got it, but then it all got flipped in your head and you couldn't exactly quite figure out what was going on with all of this stuff. Okay, so there are two definitions. You get your Arrhenius definition and then the Bronsted-Lowry definition. The Arrhenius acid is something that starts with hydrogen. The Arrhenius base is something that ends in hydroxide. This is the definition that most people know. Starts with hydrogen, there's your acid. Ends in hydroxide, there's your base. That's the Arrhenius definition. Bronsted-Lowry takes it a step further and says, okay, we have to actually look at it in a reaction to see really what's actually going on. Okay, so for example, if we have something like H2SO4 plus H2O, which then gives us H3O and HSO4 like this. Okay, if we have this equation, pay close attention to what's happening to a hydrogen ion. It's all about where's the hydrogen going. Okay, watch. H2SO4 becomes HSO4. This is losing a hydrogen. It is donating that hydrogen. It is giving up that hydrogen. However it is that you want to define that or describe it. It's going from 2 down to 1. It's lost that hydrogen. That means this is the acid. And it also means, and here's where most of you got mixed up. This is the conjugate base. The acid pairs up with the conjugate base. It's not acid conjugate acid. It's always opposite stuff. Acid conjugate base. Okay? Now, let's take a look at H2O. H2O becomes H3 hydrogen, right? It goes from 2 to 3. It's received that hydrogen. So by definition, this is the base, and this is the conjugate acid. Now, If you need me to explain why this is conjugate acid and conjugate base, I will do that right now. Okay, it's not just simply memorizing what pairs up with what. Read this reaction in the opposite direction. Look, H3O becomes H2O. Here in that direction, the H3O is losing a hydrogen. So much like how here, that lost a hydrogen going this way, going the other way, this is the one losing the hydrogen. That's why this is acid here. But it's conjugate acid because it's on the product side. Acid and base are only found on the reactant side, the left side. And then the conjugate acid, conjugate base is only found on the product side, the right side. Okay, but going this way, the H3O loses the hydrogen. Going this way, HSO4 becomes H2SO4 and it gains the hydrogen. That's why this is the base. So according to the Bronsted-Lowry definition, if it gives a hydrogen, it's an acid. If it receives a hydrogen, it's a base. Okay, let me come up with another example here. Let's say we have NH3 plus H2O, and this gives us NH4 plus H plus OH, like this. This is what's going to happen here. So NH3 becomes NH4. Therefore, it has received a hydrogen, making this the base, making NH4 the conjugate acid. H2O becomes OH. It's lost a hydrogen, making this the acid, and this is the conjugate base. Now, if we read it backwards in the other direction, NH4 becomes NH3. It loses that hydrogen. That's why it's an acid. OH gains a hydrogen to become H2O, making that the base. But since they're on the product side, it's conjugate acid, conjugate base. Okay? Those are the definitions. Make sure you have those definitions in your head. Don't get them switched up. Okay? And then, so there's really then only two more main concepts when it comes to acids and bases. So we got neutralization, and then we've got all the pH. Oh, no, there's three. And then the strong versus weak. Okay? So let's go through all of that. Let's start with the strong versus weak. Okay? So here is the pH scale. Remember, it is 0 to 14, with 7 right in the middle. And then this is 3, this is 11. Okay, this one I'm going to show you. Remember, this is just a guideline and does not always work out. Okay, so over here we have our strong acids. Here's our weak acids. Here's our weak base. And here's our strong base. Okay, but while this mostly works out to being true, it is not always true. Okay, because pH is actually a measure of concentration, whereas strong versus weak is referring to what does that substance do when it goes into water. Okay, so in order to identify strong versus weak, what we are really looking at is its electrical conductivity. The better conductor it is, the stronger it is. The less conductivity you have, the weaker it gets. Okay, so just to give you a visual image, so if this is our beaker and I'm putting in something like HCl, well, hydrochloric acid is a very strong acid, meaning that when it goes into water, it immediately well, that's weird. Uh-oh. Oh, there we go. I'm back. Sorry about that. I don't know what happened there. Completely splits right here, meaning that this is a strong substance. Okay, this is strong. Okay, acid, but you can also have a strong base, like sodium hydroxide is a strong base. And so if you put sodium hydroxide in, it'll all be a bunch of sodiums and a bunch of hydrogens all going around. Okay, no compounds. A weak substance like HC2H3O2, this is acetic acid, otherwise known as vinegar. This is a weak acid, not for any other reason than the fact that it, when it goes into water, it's only going to partially ionize. So we've got some compounds and then some ions, like this. Okay, some compounds, some ions. That's partial ionization, and that is weak. Okay, that's so that's the strength. It does kind of lead us into the pH stuff. Okay, so pH equals, and this is also on your reference chart. Okay, which here we go. So it's on the reference chart. It's right here at the bottom. Okay, so pH equals the negative log of the hydrogen ion. Okay, but the good news is that instead of having to like really worry about what this looks like mathematically, the it's really all about using your calculator. It's knowing that log button. You start with the button, you make it, you hit the negative button to reverse the charge on it. There's your pH. If you're going the other direction, you start with pH. You actually are going to do the opposite of that. So instead of log, you do second log, which is actually 10 to the x. So you make it negative, 10 to the x, boom, you're done. Okay, here's the thing about these calculations and about using the calculators. Yes, it's an exam. Yes, we expect you to be able to calculate everything on your own. But we do not want you to miss it because you don't know how to use the calculator. Not, okay, notice how there's a distinct difference there. I'm not saying that you don't know what to do, don't know how to do it with the specific machine that's in front of me. Therefore, if you're in the middle of this and you suddenly just forget how to use the calculator, please ask for help. Okay? We do not want you to miss something because you don't know how to use the calculator. We are testing you on your ability to know chemistry, not your ability to use that specific version of a scientific calculator. Okay? Hopefully I shouldn't have to say that again. Okay? So P equals the negative log of the hydrogen concentration. So that's just using the log button or using the anti-log button, depending on which way to go. The other thing to remember, plus OH equals 14, meaning it is very, 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 very simple. In the two, you do 14 minus the one that you've got, and there you go. Okay. And again, because the purpose of this live stream is just to do an overview of the entire semester, if you're wanting specific help about how to do pH calculations, go back and find that specific video, go through it, post a comment on the video if you need extra help with it, okay? So that's the last little thing. The last main concept is the neutralization reactions, okay? So for neutralization, just remember it's going to neutralize, right? So that means that one of the products is always going to be which is the only neutral substance. Okay, so let's say we have something like potassium hydroxide and carbonic acid. Well, the first product is always H2O. Always. Every time. It's a neutralization reaction. Okay? So it's always going to be H2O plus 2 ions that are left over. So here we've got potassium, and we have to look up the charges. Potassium is +1 because it's in group 1. Carbonate, remember it's on the back of the periodic table, it's the polyatomic ion. It has a charge of -2. So if we have a +1 and a -2, we're going to switch those charges and we get K2CO3. Okay? And then we balance, always starting with the non-water product. So we got 2 potassium, okay? One carbonate, so we're good there. And then I'm going to see, all right, well, I've got 2 oxygens here. So that means I'm going to have 2 waters. And just to show you that that works, 2 times 2, I'm sorry, we got 2 hydrogens there, plus another 2 hydrogens there. That makes 4. 2 times 2 is 4, so the hydrogens are balanced. But you don't have to look at the hydrogens because all you got to look at is the number of oxygens right there in hydroxide. Okay, let's do one more example, and then we will close it out. All right. Okay, so let's say we have something like, let's do everybody's favorite acid. Well, not everybody, but you know, if you're into dynamite and blowing stuff up, HNO3, nitric acid. Nitric acid is found in dynamite. It's pretty dangerous stuff. In fact, this is one of the few substances that I am honestly terrified when I'm asked to handle it. I've had to do it a couple times. I don't like doing it. it's some nasty stuff. But anyways, that's irrelevant to what we're doing right now. So HNO3, let's say, and then we're going to react this with something like magnesium. Okay, what are the products? Okay, well, let's think about it. It's a neutralization reaction. So the first product is always going to be H2O. Okay, the other product, well, what's left over? And magnesium. Which one's going to go first? The positive ion. Well, nitrate has a charge of -1. Magnesium has a charge of +2. So magnesium's going to go first. So we've got Mg, but since that is +2 and that's -1, that means I need 2 nitrates. So MgNO3, 2, like so. I got 2 nitrates. There's only one there, so I'm put a 2 right there. 1 magnesium, so we're good on that. How many oxygens are in hydroxide? Well, that is 2. Boom. Done. Okay. Fun fact, the guy who created TNT was depressed because of how his inventions put. Oh, well, that's not so much of a fun fact. That's an interesting thing to learn. Well, thank you for sharing that with all the rest of us. Okay, so and there you go. That's the entire second semester, roughly compressed down to about an hour and 10 minutes. So I hope that was helpful. By your comments here, it seems like it was pretty helpful. If you have any other specific things, please go back onto the rest of the channel, find all the other videos, find specific stuff you need, those, or send me an email directly so that I know specifically how to help you, or show up tomorrow morning, and then we'll be good to go. And then that's the end of the year. And then you guys are going to go your way. I'm going to go my way. And so Thank you guys for a great year, and I wish you the best of luck on your exam. Later.